Okay, so we learn about Newton's Cooley law differential equation. Now let's learn what we have used in this course. First, when we look at a differential equation, now this is the model for Newton's Cooley law. Is this differential equation linear? We talk the linearity with respect to dependent variable. So the decrease of the dependent variable, so t and its derivative, so we have only first derivative here, degree of them should be 1. Power of them should be 1 in order to be linear. So here t to the power 1, good. This is t derivative to the power 1, good. So it's linear. T sub m and k are constants. Okay, they are numbers. So that doesn't affect to our linearity. So this is a linear first order differential equation, right? The highest derivative you have taken is 1, so it's first order. Other thing is that is this an autonomous differential equation? This is an autonomous differential equation because the right hand side is only made up of dependent variables, or you cannot see the independent variable explicitly. Here the independent variable is time, simple t, and you don't have it on the right hand side. Okay, so this is an autonomous differential equation. Now, is this homogeneous? This is a non-homogeneous differential equation. Substitutes t is equal to 0. So when t is equal to 0, dt over dt is equal to 0. So you have 0 is equal to k, 0 minus t sub m. So 0, this is negative KTM. So 0 is equal to negative KTM doesn't make sense. So this is a non-homogeneous differential equation. Okay. Now the other thing that we learn is how to solve a differential equation. The methods that we learn are separation of variables, and we learn integrating factor method. Can we use one of those methods to solve this differential equation? Well, it turns out that we can use both separation of variables and integrating factor method to solve this Newton's Cooley law differential equation. Let me show you how to do it with the separation of variables, because that's the easiest of methods. Okay, to do the separation of variables, we have to take all the dependent variable terms to the left. So dt over, I have to take t minus t sub m terms to the left, and let's keep k other side because you don't have to take it to the left hand side and it doesn't have a capital T term. Now we do an integration. So integral of t minus t sub m is natural log t minus t sub m. Okay, so let's use open brackets, and this is k times simple t plus a constant c. Now what you do to get the explicit solution, we take the exponential power of the right hand side. So it's e to the kt plus c. We can break plus c. Now we have seen it so many times. E to the c is an arbitrary constant. Okay, so we can write it as c times e to the kt. So finally, let me write the answer here. T is equal to, let's take t sub m to the other side. So t sub m plus c e to the kt. Now this is the solution to the differential equation, Newton's Cooley law. Very easy to solve. Okay, all right. Now I'm not going to do how to solve it from integrating factor method, but that is something you should do once in a lifetime, because when you go to the exam you cannot memorize this solution. Sometimes, depending on the instructor, they might ask you to solve the Newton's Cooley law differential equation. So you have to know how to solve it. So if you mess up on separation of variables, you have another method to solve the differential equation, which is integrating factor method. So I highly recommend you to read the note and understand how to do it. Okay, it's very easy like separation of variables. Now what I'm really interested in is analyzing this differential equation. So let's take an example. Two thermometers reading two different types of temperature values taken into the room with a temperature of 30 Fahrenheit. So we have a room with a temperature of 30 degrees. So the differential equation is T minus 30, ambient temperature is 30, and they say K is negative 0.03. Okay, so this is the model. Now, if we think about what we learn on chapter 2.1, the slope fields, one thing that we asked is what are the equilibrium solutions? So what is the equilibrium solution here in this example? Well, to find the equilibrium solution, what you do is you make the differential equation equal to 0 and solve for t. So you have to make 0.03 t minus 30 is equal to 0. You solve for dependent variable. Here you get 0 when t is equal to 30. So equilibrium solution is actually t is equal to 30. Or in generally, what is the equilibrium solution? Ambient temperature, right? T is equal to T sub m. Now, in the physical meaning of the equilibrium solution, physical meaning is, what is 30 means here? Physically, 30 means that the room temperature is 30. Your thermometer, if your thermometer reads a temperature less than 30, what happens is, your thermometer will eventually read 30, right? And nothing more, nothing less. If your thermometer reads more than 30, okay, and it will decrease down and read 30 eventually, right? It's like a cup of coffee versus an ice cream, right? Now 30, the equilibrium solution, means the stage where your temperature doesn't change. Think about it. You bring a coffee that is higher than 30 to the room, and when the coffee cooled down to 30 degrees, nothing happens after that, right? Neither the temperature going to increase, neither the temperature going to decrease. So equilibrium solution is a solution where nothing changes. Okay, that is what we meant by rate of change is 0, right? Rate of change is 0 means no change happened. So that's the physical meaning of equilibrium solution. And we call these equilibrium solutions, or this type of no change solution, steady state solution. So that's something you should take note of. Steady state solution. Steady state solutions are solutions where no change happened, just like equilibrium solution. Okay, now if we draw the slope field manually, we can draw it. So equilibrium solution 30 means, or let's generalize it, T sub m, ambient temperature, think it as 30. Now it is an equilibrium solution, means no rate of change, physically nothing change, and mathematically slope field wise your slopes are horizontal, right? Now it all makes sense, right? It's all seems to be tying together. Now what happens if you are in the region here? Well, your temperature starting to increase until the room temperature, right? This is how it should look like. And then what should happen? Your slope should gradually, get horizontal, right? So that is what happens in the slope field. So if you look at the slope field at 30, you have horizontal flat slopes. Oops. Right, flat slopes. And then you can see the solutions. So if you start with a temperature of 0, what happens is you approach 30, but nothing more than that. Now if you start from a temperature higher than 30, you approach 30 and nothing less than that, right? So gradually become horizontal. The slopes gradually become horizontals. So this 30, of course, is the equilibrium solution. Okay, and now it all, I guess, makes sense. Now the other thing we need to discuss, what we had in our language, is when you talk about equilibrium solution, we ask the question whether it's stable or unstable. Now this also have a physical meaning, right? So what do you think this 30 equilibrium solution, T is equal to 30, or generally for any model T is equal to T sub m, what do you think? Is it stable? It is stable because you approach towards 30 from both sides, right? So T is equal to 30 is a asymptotically stable equilibrium solution for Newton's cooling law. So ambient temperature, the room temperature, the eventual temperature, many names, right? Steady state solution, equilibrium solution is an asymptotically stable solution. Okay, so that means it has a physical meaning. That means you come close to the room temperature. Okay, let's say you have an ice cream and it gets warm and it comes close to the room temperature, and like at 29.9 your ice cream is not going to get again to the freezing or again going to cool down, make a change. It's not going to happen. It's stable, right? The room temperature is stable as long as you don't change the room temperature. So our assumption here is the room temperature doesn't change, right? So that's what's going on. So that's the meaning of the asymptotically stable equilibrium solution. So in this case, the eventual temperature in the example that we show is 30 degrees, right? Okay, now the other thing is we discuss about equilibrium solutions, ambient temperature, and the other thing we need to discuss is K. Okay, now K is the proportionality constant, and we say it depends on the material properties. Now think about this situation. You have a cup of coffee again and you want to go to work. Let's say you take this cup of coffee and you put it in the thermostat, where this thermostat will keep your coffee, warm. Now, this does not obey Newton's cooling law, right? This situation. Your coffee is inside this thermostat and you are carrying it all the way, to a room, to outside. The coffee is not going to, cool down. It's going to stay hot because of the material properties of the thermostat. That is where this K comes into play. Okay, so your thermostat materials, the material that this thermostat is made of, effect to this K. So it makes the rate of change, d over dt, very small. Okay, it makes this guy very small, the surface of the thermostat. And the other thing you might think, where the Newton's cooling law is not perfect, you take a cup of coffee again and think what happens, a hot cup of coffee, okay? Think what happens if you stir it from a spoon. Now, when you stir it inside the room from a spoon, the temperature, rate of change, guess what happens? The rate of change of temperature is going to be higher because the metal spoon, if it is a metal spoon, it's also a source where you can pull out the heat very quickly. Metal is a good conductor, right? So it's going to take the heat out of the coffee very quickly. All right, so that is where another place where K comes into play. So depending on what K you have, you might have different solutions. So you might start from here, for example, you might start from a temperature of 70, and this let's see, the red color represents the K. The blue and the red color represent the K for negative 0.02 and the blue color is negative 0.03. Now different Ks, but the different K values, okay, but the same starting temperature with the same room temperature. Let's say you can see the rate of change of the temperature is different. Okay, so this K is going to definitely have a effect on how the rate of change happens. So that is what we have to discuss about Newton's cooling law. How to solve a full problem from Newton's cooling law. There's one problem in the quiz, and I have you have a mini video built onto it. So we wanted to discuss the properties about the Newton's cooling law, and I highly suggest you to read the full note and make the connections from the stuff that you learn from the beginning of this course. Okay, all right, thank you.